Alrighty, we are back with our second day of our proof chapter. So we are doing 4.2 today. Yesterday, we talked about congruent polygons, and then we talked about ways to prove that two polygons were congruent. And that is what we have right here. But first, let's go ahead and jot down what the name of this section is. This section is called S, 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 and S, A, S. Okay. So the start thinking part says, in order to prove that two triangles are congruent, so far, you must show that all corresponding sides are congruent and all corresponding angles are congruent. So once again, there are three sides and there are three angles. So we would have to show that six different pieces are congruent to six different pieces, and then we can say that the two triangles are congruent by definition of congruent polygons. Okay, you guys are mathematicians in the works, and one of the things I want you to be always thinking about is there a more efficient way to do this? There's got to be a more efficient way. So what we do with math is right now we're at the point where we have to check six different things. Okay? Mathematicians start thinking, is there any way we could check less than that? Is there any way I could just check the sides, or just check the angles, or check two angles and a side, or two sides and an angle? I really don't want to have to check six whole different things, so maybe I can just check some of them. So basically what we look at here is we try to figure out, is it possible to make more than one triangle with these set of characteristics? If the answer is no, if there's only one possible triangle that can be created with those set of characteristics, then that's enough to prove the two triangles are congruent. So if we look at this first one here, it's called SSS, or side, side, side. Let me go ahead and explain that to you really quickly. If you had a triangle that was 3 inches, 4 inches, and 5 inches, and then someone else was supposed to make a triangle that was 3 inches, 4 inches, and 5 inches, but you told them that they could do anything they wanted with the angles, and both the people went over and created the triangles. This one would look something like this, and this one would look something like this. What ends up happening is you find out, if you know the side lengths, there is only one possible triangle that can be created. Okay, both of the triangles would look exactly the same and would be congruent. Now, the reasoning behind this is that we say that triangles are rigid objects. It means if you got a triangle, let's say you had this triangle and you pressed really hard on it this direction, it wouldn't deform. Okay? Let's think about other figures and figure out if just knowing the sides are congruent to the sides, if that would be enough. So remember, the deal is, if you can make more than one figure with those characteristics, then it's not enough. So let's say you had a four-sided figure where the side lengths were 4, 4, 4, and 4. Okay? Is there any other possible shape that this could be, but also have the side lengths of 4, 4, 4? Well, yes, there is. Imagine I went over and made this out of straws, and I went over and pressed in that direction. What would happen is the figure would deform. It would keep its side lengths, but the angles could change. It would still be 4, 4, 4, and 4, but you can see that this figure is not congruent to that. It's not identical in form. That is because quadrilaterals are not rigid objects. If you go over and press on them in a certain direction, it will deform them. If you got a triangle and you made it out of straws and you pressed really hard in that direction, you might be able to bend the straws, but if you don't bend the straws, the shape cannot change. Okay? This kind of explains why we use triangles so much. What I mean by that is, if you went over and made a bookshelf, you almost never make a bookshelf that looks just like this. A lot of times what people will do is put a little cross member here, okay, a little piece of wood that goes across. The reason why they do that is because they go over and are basically creating a triangle, and a triangle is a rigid shape. If you just had a bookshelf that looked like this, and you pressed on it in this direction, once again, it would deform. It would look like this. It would look um, more like, I know that a rectangle is a parallelogram, but it would change its shape. If you went over and made this cross member and you have the triangle inside, it is going to be a rigid shape now because it has the triangle in it. And if you pressed really hard in this direction, it couldn't change because the triangle is a rigid object. All right, so what we just learned is that since there's only one possible triangle that can be created with a side, a side, a side, knowing those lengths, then all you have to do, one of the ways, the shortcuts to checking if two triangles are congruent, is just looking at the sides, aka the SSS postulate. If three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. Okay, so if, let's say I had these, that's congruent to that, this is congruent to this, and that one is congruent to that one, then the triangle is congruent to the triangle. So you could finish your proof. If you're trying to show that they were congruent, you could finish your proof with SSS. I'm just telling you right now, we'll never again finish a proof with definition of congruent triangles. Now, one other thing to note, SSS works with triangles, but SSS, if you threw an extra S in there, would not work for four-sided figures. You would actually have to check all the sides and all the angles. Okay, so let's keep on going and take a look at an actual proof. So if we looked at this right here, and we knew it was given that this was congruent to this and that one's congruent to that. Ooh, we're only one side away from knowing that the two triangles are congruent. Once again, we do not have to check a box off for all the sides and all the angles anymore. One of our shortcuts is SSS, so we're kind of hunting in that direction. Is there any way to show that the third side is congruent to the third side? Look at this. This side is shared by both of them. Well, we definitely know that the LN side on triangle number 1 would be congruent to the LN side on triangle 2, which means that the third side must be congruent. So let me show you how you would do this. You'll see it's much quicker than what we were doing in the last lesson. You would say LM is congruent to NP, LP is congruent to NM, both of those are by given. I now have two of the three S's that I need. My last S is just going to be stating that LN is congruent to LN. That's basically saying one side of that triangle, LN, is shared, and LN is the side of the other triangle as well, so they must be congruent, and it's the reflexive property. We have an S, we have an S, and we have an S. Awesome, so we can be done. Triangle LMN is congruent to triangle NPL. Ta-da! So, hopefully that made sense to you. Let's keep on moving on. Okay, this side is congruent to that side. That's one S. That side's congruent to that side. Ooh, look, we have the reflexive property. Remember, the reflexive property is when you have a side or an angle that is shared by both triangles. So this is pretty much an identical proof. We could say BC is congruent to BF and CD is congruent to FD. That's given. That's two of our S's. And now BD is congruent to BD. That's one side is congruent to its corresponding, another side is congruent to its corresponding, and the last side is congruent to its corresponding. That is by the reflexive property. And now we can finish it. Triangle BCD is congruent to triangle BFD. And the reason? Side, side, side. Everybody knows what SSS means when you're doing a proof. So you don't actually have to write out side, side, side. want to remind you why this works, because there's only one possible triangle that can be made if you knew the lengths of all three sides. Only one possible one. Okay, so let's move on. The next one is SAS. Okay, so I'm going to go ahead and draw it. Once again, we are wondering if I knew a side, then an angle, then a side, how many possible triangles could be created? Let's try it. Let's say you had 3 inches, a 40-degree angle, and then 5 inches. 3 inches, let's say, was that, a 40-degree angle, which is like here, and then this would be 5 inches. How many possible triangles can we make with this? Well, it's basically, you don't have a choice. This side must be this length, and all of those angles are kind of locked into place. There is no way to go over and make another triangle that looks different than this one if this length was 3 inches, this was 40 degrees, and that was 5 inches. It kind of locks all the rest in. Since there's only one possible triangle that can be created with a side length, then an angle, then a side length, then SAS is enough to prove two triangles are congruent. If you were on the phone with your friend and you said, I don't know if my triangle is congruent to your triangle, and they said, I have a side length of 5 inches, a 50-degree angle, and then a side length of 8 inches, and you go, oh, I have the same. You don't have to ask any other questions. You know for sure the triangles must be congruent. So let's go ahead and fill out what SAS means. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, and the triangles are congruent. Now that's super important for you to understand. The angle has to be between the two sides. So if you had like this one and this one, that was congruent to that, this one was congruent to this one, and this angle was congruent to that angle. It's a side, then an angle, then a side. Notice the angle is between the two sides, and the angle on this one is between the two sides. In that case, then you know the two triangles are congruent. Now, sometimes you have these problems like this, and it says, what other information do you need to be able to prove these are congruent by SAS? So right now, we know that this is congruent to that. Now, the freebie one is the reflexive property. So if I redrew these, it'd be this triangle, be this triangle. We already know that that is congruent to that, and these would be congruent by the reflexive property, because really they are the same side. So what else would we need to know? We have, and we're trying to do it by SAS, we need to know the angle between the sides is congruent to the angle between the sides. So we would need to know that that angle is congruent to that angle. So what extra information do we need to know? We would need to know that angle EFD is congruent to angle GDF. And then that would be enough information for us to figure out the proof, or finish the proof. Now this is a big skill to have when you're trying to learn proofs, because how this works is you have givens and you have easy things, but if you knew you were trying to go in the direction of, let's say, SAS or SSS, then you could say, I wish I had one more piece of information. For example, if this said you would want to do it by SSS, we have two sides. We wouldn't care about this angle. We would want to know that that side was congruent to that side. And once you know what you need, you can start looking at your geometry toolbox and see if there's any way to get that information. Now this one right here, we want to figure out what other information do we need. We already know that this angle is congruent to that angle. Reflexive property says that those are congruent. So let me go ahead and just redraw them, not interlocking. So it might help you out a little bit. We knew that that angle was congruent to that angle. This side was congruent to this side because really they're the shared side. So we have an S and we have an A. We're trying to finish by SAS. What is the last side that you would need to know was congruent to another side? Well, it would have to be this one congruent to this one, because then you have an S and an A and an S. So you would need to know LE was congruent to NB. If you knew that, then you'd be able to finish your proof. So let's say this was an actual proof we were doing, then you start putting all of your effort at trying to figure out, how could I go over and show that these things were congruent? Now, let's look at these problems. These are kind of cool. It just says, is there enough information to determine that the triangles must be congruent? If so, why? Would it be SAS or would it be SSS? What would be your reasoning? So take a look at this one. Do we have enough information here to do SAS or SSS? I see one tick and a two ticks. This one also has a one tick and a two tick, so that's that pair of sides, the two pairs of sides that are congruent, and the angle is between the two sides. So there is enough information. We would be able to show that those two triangles were congruent by SAS. Now let's look at this one right here. Is there enough information to show that these are congruent? Well, it has the one tick and the one tick. Those are congruent. Two ticks and two ticks. So we have the two pairs of sides. Oh, look at this. Where is this angle located and where is this one located? That one is located between the two sides, which is what it should be. This one is not between the two sides. So this one would be not enough information. I hope that's making sense. The angle has to be between the two sides. So the next one, we have this side is congruent to that, this one is congruent to that one, and this one is congruent to that one. Well, it looks like you have a side congruent to a side congruent to a side for the two tick marks, and the last side congruent. Is there such thing as SSS? Yes, there is. So we don't even have to look at any of these angles because we know there's only one possible triangle that can be made with those side lengths. And what I mean by one possible triangle is like visually looking at it. Obviously, these are two different triangles, but they're congruent. I'm saying that you couldn't change the shape. There's only one shape of that triangle that you could have with these side lengths. Now let's look at this one. Well, I see one tick and one tick, two ticks and two ticks, three ticks and three ticks. So definitely by SSS. Is there any other way that you could do this? If you looked at your geometry toolbox, is there anything else that is embedded in this problem? Do you see linear pairs or what could we use? Knowing that we're trying to look for sides or angles that are congruent to sides or angles. Look at that. I told you that this would show up all the time. Those angles must be congruent because they're vertical angles. So SAS would also work. Because look, the angle is between the one tick and the two ticks, and over here it's between the one tick and the two ticks. So this one could be SSS or SAS. If I was to do this problem, I would have done this. Why? Because I would just state the givens and finish with SSS. This one involves you having to use something that is not flat out given. It's the vertical angles theorem to be able to do it. Now on this one, it says, which one, if not both, would you use? Can we use SSS? One tick, two ticks, two ticks, three ticks, three ticks. Yep, SSS would work. Can I use SAS? Ooh, SAS. Why can we not use SAS? Well, take a look. This angle is between the two ticks and the three ticks, whereas over here, that angle is between the one tick and the two ticks. So the angle is not in the same location. So SSS would be the only way we could do this. All right, let's move on. Take a look at some more proofs. I've got 3 proofs that we can do. Okay, so on this one, we are trying to finish with either SSS or SAS. Well, I like SSS, so let's try that. Let's think through this and see if we can do SSS. We have that side congruent to that one. I see the reflexive property. And then we would need to know that side is congruent to that side. How could I do that? We can't. We don't have anything. So even though I really wanted to do SSS, I now have to abort mission and try to figure out, can I do SAS? What did I tell you guys? Pretty much always when you see parallel lines, you know you're going to be doing alternate interior angles theorem or something like that. So is there any alternate interior angles theorem here? Those would be my lines. That's like that thing that's cutting through. These are parallel. Oh yeah, look, this angle is here, and this one is here. Okay. So we should be able to do this problem because we're going to be able to have, if I drew out my 2 triangles, oops, didn't draw that very good. Let's say we had this. We're going to have reflexive property given alternate interior angles theorem, and that would be SAS. So let's go ahead and do this. AB must be congruent to CD. Why? Given. That's my S. You don't have to list it in the S, then the A, then the S. You could have done both S's and then the A in your proof, and you wouldn't get any points taken off. I'm going to do it in order just so it's not confusing. Now we know that AB is parallel to CD, given. If that's true, then I must know that angle ABC is congruent to angle DCB by the alternate interior angles theorem. And then my last S is the reflexive property. CB is congruent to CB, reflexive. And now we can finish our proof. Triangle ABC must be congruent to triangle DCB by SAS. Here was your S, here was your A, and here was your S. SAS. All righty. So there was a legit proof, and it was pretty hard because this was not given. Or this was given, but that's not exactly what we wanted to use it for in the proof. We had to state that and then be able to use the alternate interior angles theorem. All right, let's keep on going. We're not going to do the crazy hard proof at the end. We're going to do these 3. I think that should be enough. All right, SAS or SSS. Which one are we going to do? I see an S, another S. Woo! If I could just show that that side was congruent to that side, then I could finish my proof with SSS. But I can't think of any way to show that those are congruent. Okay, so SSS seems to be out. It's going to probably be that. Well, they say that this is perpendicular to that, and this one is perpendicular to that. So knowing that they're perpendicular is that we know that these are right angles. If you looked in your geometry toolbox, is there anything you know about right angles? Let's see if I can bring it up. What do we know about right angles? Oh, number 18. All right angles are congruent. Oh, yeah, okay. So I know that all right angles are congruent, which means that must be congruent to that. And beautiful. Now we have 2 sides and an angle between. We'll be able to use SAS. So let's go ahead and do this proof. 1S is AC being congruent to B, that's BE. given. That's my S. Now let's do the angle part. We are going to put down AC and BF are perpendicular to CF, given. Now you're going to see how we have to do this in these proofs. We cannot just jump to saying they're congruent because we don't even know they're right yet. What we would say then is angle ACD and angle BED are right. And that's just definition of perpendicular. How did I know that they were right? Because I already said they were perpendicular. And now I could say angle ACD is congruent to angle BED because all right angles are congruent. We have my S, we have my A. Let's do the last S. CD is congruent to DE, given. SAS, done. Triangle DAC must be congruent to triangle DBF. That would be SAS. Fantastic. Now this is a little tricky right here, but know that a lot of times with the proofs we're doing right now, if they say things are perpendicular, for the proofs we're doing right now, you're most likely then going to say that the angles are right and that therefore the angles are congruent. In later proofs, we might switch that up a little bit, but not in these ones. Okay. Now for this last one, how are we going to do this? That's congruent to that one. Now they say C is a midpoint of BD, so that must be congruent to that. And I love SSS, so if I could just show that that is congruent to that, then we could finish our proof with SSS, but I have no way of doing that. So as of right now, it looks like SSS is out. SAS seems like it's possible. Is there any way to show the angle between the two sides are congruent? Yes, vertical angles theorem, VAT. Cool, so we already know how we're going to show an SAS. So first, AC is congruent to CF given S. I'm doing it in order just so you don't get confused. Angle ACB is congruent to angle DCF by vertical angles theorem. That's my A. You don't have to write this down if you don't want to. It just helps me to make sure I'm not forgetting something. Now we know C is the midpoint of BD given. Therefore, I know that BC must be congruent to CD, def of midpoint. That's my other S. And now I can finish with triangle CAB is congruent to triangle CFD, SAS. All right, so we know two shortcuts as of right now. As I said, we're not going to do this crazy proof at the end, but I can go and do the wrap up. The wrap up just says you can prove two triangles are congruent by showing that all corresponding sides and all corresponding angles are congruent, or, and we'll never do that again because it's just the long method, would never, if you know that you can stop once you have an SSS, then why would you keep going to look at angles? If we're going to be efficient here, stop when you have enough information. So instead of using what we learned in 4.1, we are going to now be looking at these shortcuts, SSS and SAS. If you're going to use SAS, make sure the angle is between the two sides. All right, hope that makes sense. Here are the two shortcuts we know. You might be asking yourself, what about AAA? We'll look into it. What about ASA? We'll look into it. But as of right now, we only are sure that SAS and SSS will work. Thank you for watching. Come to office hours if you need some help.